Okay, these are some more problems from section 9.4. Again, we're trying to determine the convergence or divergence of the series, identify the tests or tests are used. There may be more than one correct way to determine the convergence or divergence of the series. So, number 31, this was n squared minus 1 over 2n. I just chose to use the ratio test. So we're going to use the limit as n approaches infinity of a sub n plus 1 over a sub n. So we'll take that ratio. So first of all, every time I see an n, I'll put n plus 1. So it's n plus 1 squared minus 1 all over 2 to the n plus 1. And then divided by this, or times the reciprocal. So just to save time, we just multiply it by the reciprocal. Okay, 2 to the n all over n squared minus 1. Okay? And n's going from 1 to infinity. So all these will be always positive, so I don't need to do the absolute value. I just need to just look at the series because they're always positive, so there's no issues there with negative signs. What we can do is we can multiply this out, and if I multiply this out, I get n squared plus 2n plus 1 minus 1 is just n squared plus 2n. And on the bottom, I can rewrite this as 2 to the n times 2, or 2 times 2 to the n. And this is the 2 to the n, and this is the n squared minus 1. And you can notice that the 2 to the n's cancel. All right? And I'll just have an n squared plus 2n. And then I have 2 times this, so that's 2n squared minus 2. Okay? Now, if we look at this and we want to take the limit as n approaches infinity, we can use a method we use for horizontal asymptotes, or that we learned from pre-calculus about the limit of a rational expression. Okay, if we have powers, if we have polynomials in the numerator and the denominator, okay, we just look at the highest degree term and the ratio of those coefficients. So the highest degree term is n squared, they're the same. If the highest degree term are the same, we just look at the coefficients of the, or look at the coefficients, the ratio of the coefficients, pardon me, and that's going to be 1 over 2, so that's the limit. So the limit of this equals 1 over 2. All right? And there's a lot of factoring. There's a lot of other ways you could do it. But we'll get 1 over 2 anyway. And that's less than 1, so that's L. This equals L. Since L is less than 1, L equals 1/2. Since L is less than 1, it converges. That's all. Okay? Now these are particular values, and these are going to come in handy when we start talking about endpoint. What's happening at the endpoint. So these are kind of getting you ready for some of the tests you use for that. Okay, on number 32, okay, negative 1 over 8 to the n. So I could rewrite this as negative 1 times 1 over 8 all to the n power, and that looks like that's a geometric series, right? Even with a negative, they're all negatives, but still, the ratio could be 1. With just a constant in front, 1/8, pardon me, the ratio could be 1/8. So since r is less than 1, 1/8 is less than 1, then it converges. That's a geometric series that converges to a common ratio. Okay? Alrighty, let's see here. Okay, let's take a look at this one. Okay, now, like I said, there's more than one way to do these, but again, if you look at this one, this is going to be less than, if I make the denominator smaller, then the result will be larger. So if I make this smaller, or subtract that, then this result will be larger, so that means that 2 to the n over 3 to the n is larger than this, right? Because what I do is if I make the denominator larger, I make the result smaller, you see, so smaller, larger. And then this, so that means that it's less than every term. Now this is a geometric series, isn't it? Because I can rewrite it as 2/3 to the n. So it's a geometric series. And what's r? r is 2/3. So r is less than 1. So since every term in this series is less than every term in this series, which is a geometric series, this converges by the direct comparison test. Direct comparison. And sometimes you just have to be aware of that fact that if you make the denominator, okay, smaller, you make the result bigger. So you have to be careful on that to keep that squared away. Okay, number 34. Now, here we're going to take a look at the nth term test because we've seen this one before when we were doing limits. This is a kind of a classic limit problem. So if I take the limit as n approaches infinity of this, we always have problems with this oscillation and 1 over the n. So remember what we did was we let t be 1 over n. Therefore, n equaled 1 over t. Hope you remember this little technique we use for this limit. So as n approaches infinity, as that approaches infinity, 1 over infinity approaches 0, so t approaches 0. So I can rewrite this limit as n approaches infinity of n sine of 1 over n as the limit as t, do it all in terms of t approaches 0. And what was n? N was 1 over t, and the sine of, and what was 1 over n? T. Now, if you remember, this is going to be the limit of the sine of t over t as t approaches 0. You can use L'Hopital's rule to show that this is going to be the cosine of t over 1, which is at t, if I substitute 0, I get 1. Or we just remember that this limit was 1. Okay, so since the limit, okay, of the as the terms approach infinity, as n approaches infinity, does not equal 0, but it equals 1, then it diverges by the nth term test. All right? Because if it does converge, the limit of the nth term must be 0. If the limit, therefore, by using the contrapositive, if the limit of the nth term as n approaches infinity is not 0, then it does not converge. Okay? So that's your good old nth term test. Okay. Okay, well, those help. We'll do a few more in a moment.